dear colleagues, we continue our seminar, all Russian seminar on optimization, and today we have a talk of worldwide known scientist Angela Nedich in distributed optimization. Angela is a PhD student of Vasilyev Fyodor Pavlovich and Bertsekas, Dimitros Bertsekas also at the same time. He obtained a PhD degree in Moscow State University, and then he obtained another PhD degree at MIT, yes?
Yes.
Oh, she. Okay, so Angela, please start.
Yeah, good morning, good afternoon. I'm very happy to be here, and I'm very excited to see that actually my Fyodor Pavlovich is here. Sorry, I want to greet Fyodor Pavlovich Vasilyev. I see Mikhail Potapov, and I also see my professor from Montenegro, Milovica. So special greetings to them. Okay, so I'll present. Oh, sorry, I'm already making mistakes. I will be talking today about distributed optimization methods in networks that we have spent quite some time investigating over the past many years. So the work really is, I'm going to talk is going to be discussing some of the things we start working long time ago. It's almost 10 years, and then go into more recent advanced developments. I got a little bit, I guess, emotionally disturbed, so I lost my focus. Okay, so let me get there. So what are we going to consider? I'm using a prototype problem which is very popular these days. It's sort of a problem that appears often as a machine learning problem, when you actually, your job, your task is to optimize a sum of collection of functions, where we assume in this setting the functions will be convex and differentiable, so we are going to work with a nice case. We assume that there is, let's say, m components in this sum, and the vector dimension is n. So the part that we want to do that's somewhat different from, meaning this problem wouldn't be interesting. These days it's interesting because m is considered very large and there are a lot of works in that direction. What we are going to consider here is also the case when there is a network. So these m, we can think of them as m agents or m nodes that are in the network. Let's say, consider for time being the network that's connected and undirected. And in every node, you have this, every node has its own objective function. So the goal would be to solve such a problem given the constraints of the communication constraints that are imposed by the network. So what we mean by that is that, for example, agents here, agent I that holds a function fi, the agents do not share the function knowledge. So they will be willing to share some information between each other along the existing links and only with the immediate neighbors. And the problem is now to solve this problem, given this constraint, solve it distributedly, which means obey the structure of the network, who can talk to who, and solve the problem without disclosing the functions, revealing information about the functions itself. And the part, basically what means we are not going to allow to have a central entity in the network, which will be, in general, that would mean that I have one node that can collect information needed from every node, do some computation, and send the updates back to the nodes in the network. So we are not going to, we are eliminating this central coordinator. So we are just looking at the execution of some algorithm that can solve the problem where all the connection, all the information exchange is just local in the network, one-hop neighbors. So as I mentioned, this problem is, meaning when we want to concretely connect with machine learning problems, this problem often arrive when you have collection of data, so that the F function, for example, Fi here can represent the loss associated with some collection of data that's available to agent I. And for example, one concrete example is if you look at some problems, let's say when you're just looking at the data that has two labels, so it's a binary label, let's say you are really looking as what they call it, like a binary classifier. So you are trying to find out some hyperplane that separates the data in a certain way, then the objective function at agent I would be reflective of the collection of this summation is collection, it's a sum of the losses associated with the data it has, and there is usually some regularizer, which is this rho of X, which is usually helping us stabilize and find a unique solution. So one specific example is, for example, this logistic regression function, which would be satisfying the assumptions we made. But in the time when we were beginning to work on these things, our kind of sources of that who could benefit at the time were not really problems that are nowadays picking up. The problems were coming more from the sensor systems, and we did some simulations when they are really small academic simulations, but the applications were more into kind of source localization, then scheduling kind of power in a mobile devices, or even looking at this kind of hypothesis testing based tracking, which Caesar actually had done some of it. These names that appear, those are my former PhD students that were actually picking up on these applications, and I learned the applications from them. They were the ones who were really doing that, I would say, more applied and well and connected to the reality. So I'm gonna now go back to the problem and try to think, saying how we're gonna solve it. Meaning, what was the idea that we kind of used when trying to develop a process algorithm. So first we're gonna let's say we gotta get a more concrete model for the network. So what we do is that a network will be modeled by a graph. And sorry, here I have a graph with the n nodes. Actually, it should be m. That's a typo there. And given a collection of edges, where its edges are just telling us which nodes can exchange information, which are the links that exist in the graph. We'll assume the graph is connected. That will be important. So the next part is that just to bring the intuition toward how we're going to look at the algorithm, we can go for something that nowadays became a kind of a common way of how you can represent the problem to explicitly encode the information about the graph. So the way it's done is typically you make for every agent, you make a copy of the decision variable and label it as an xi. So the minimization problem is now summation of fi's of xi's, and now we are minimizing over a much larger vector of all of these xi's. However, this the objective function now becomes separable, and we impose the constraints that say basically that we want all xi, the decisions of all the agents to be the same, which is if the graph is connected, you can encode it by using the local structure, using actually the local connectivity. So what it means is you can write the constraints per node. So if for node I, you write xi is equals xj, saying the decision of the node I has to be equal to the decisions of all of its neighbors. So that part that I have underlined there, now it's equivalent to basically saying I want all the decisions to be the same. But this particular kind of constraints, when we look at them, it turns out that they have appeared in other parts of the literature for different reasons, and they can be called agreement constraints, because what you are really asking is that all the agents agree on their decisions. So I'm going to call it agreement or consensus constraint. n sub I is the set of neighbors, and I have defined it right there for the node I in a graph. Now the part is that actually when the objective functions are 0, and that's a special case, it's the problem really for time being reduces to what is called consensus or agreement problem, which is really just a feasibility problem, in which you are looking for to solve the problem. You want an algorithm that will be distributed, executed locally by exchanging locally in the network information. And the goal is to find a point that's feasible. Basically, you want to find an algorithm that will generate, every node will have its own sequence of iterates, xi of t, which are, in a way, agents talk, but we'll see that in a minute. And you want that sequences that they are constructing to, in the limit, approach some point that is the same for all of these sequences that are produced by the local algorithms that the agents are executing. And you want algorithm to be convergent regardless of initial points of the agents. So basically that problem can be solved. There are a couple approaches that one can go about it, but one of the approaches that we're gonna use is so-called weighted averaging. What the algorithm does, so now we are looking at solving this agreement problem where we are not worried about the functions at the moment, because this agreement algorithm will be important later for the construction of the minimization algorithm that will solve the problem we want. So to do that, what is the weighted averaging? Well, it's a relatively simple idea. It says that so it's synchronized algorithm, which means we have times t at which updates will be happening. When the node, when the time comes for the update, I have one equation, but it's really, there are more details around it. So what it says is that time t, every agent has already computed xi of t, and they are ready to communicate. So agent I will send its variable xi of t to everybody, every neighbor j that it can reach in one hop. And at the same time, because the simultaneous exchange comes from the other side, which means every neighbor will send its own xj of t to the agent I. So update then becomes what this relation says, the last line here. So when the agent I receives the xj's from the neighbors, and also it has its own, this is like j goes, not here, j goes from within the neighbor set, union the node itself, which means xj's from the neighbors and the xi from the prior step of the agent I is involved in this convex combination. So weighted averaging means that these weights aij that agent I decides on will be such that they are positive numbers, and also they add up to 1. So basically this here would mean that we just make a convex combination, every agent makes a convex combination of with strictly positive weights of the information on the decision variables it sees from the neighbors. And just to make the to analyze the process now that we have, makes it easier if one defines a matrix where we introduce the values aij equals 0 for the indices j that are not the neighbors of the node I, and when j is not the same as I. So you get to now a row stochastic matrix. The matrix A now becomes row stochastic, and very important, it has these positive entries are there only when the links in the network exist. The matrix doesn't have to be symmetric, but it is it has to have a positive entries on every link ij. That means aij greater 0, aj greater 0. And if now we kind of take these, I assume here that for time being, X's are just columns. So if you kind of transpose these vectors and construct a matrix X, this capital X is just now a matrix with row entries of the decisions of the agents. And becomes the iteration is really this first line, connection between all these updates at time t plus 1 and the updates at time t. They are just governed by a linear, basically linear equation where A is your matrix governing the process. So it's easy to go back, have a comma here, sorry for that, another typo. So if you go back simply, this, you get that this iterative process is basically driven by the power of the matrix A and the initial matrix that you had. So now the whole convergence of this is easy to understand because it says that we need to look at how the matrix A behaves. And when the matrix A is row stochastic and also compatible with the graph, there are a couple ways to interpret this, meaning one can talk about Perron, because this is a non-negative matrix. One can apply Perron-Frobenius theorems that applies to this case because the matrix is primitive. The other way to look at this problem, this matrix, is that imagine it's you can interpret it as a probability what is that? Sorry, I lost the word for a moment. Transition matrix for a Markov chain. And in this case, because of the graph structure and the self loops on the diagonal of the matrix that we imposed, the chain is well behaved. So it's A corresponds to transition matrix of an ergodic Markov chain. And then by the theorem of Markov chain, one can find that there is the limit of this matrix is well defined. It's given by the expression you see. It's one is the column of this bolded one is column of all ones, and pi is actually the steady state distribution that would correspond to the chain. So what we obtain is now from here, we can actually not just see that the limit exists, but we know exact. Yeah, so what we get is we also have an expression of what that, basically we know what the limit of this individual process, iterate sequences that are produced at a node I. We can explicitly find what is the really consensus point in this case. And it's given by this weighted average of the initial points where the weights are determined by this limiting probability of the Markov chain. So we have a nice understanding now of basically what this weighted averaging algorithm is doing for the consensus part. And now the construction, now we look back in our problem where we want to solve when the functions are not necessarily zero. So you want to solve the minimization of the sum. And in this case, this algorithm that we proposed quite some time ago was very simple and naive in a way of, basic idea was just combine this consensus process, which will force iterates to kind of reach the same common point, but combine it with a sort of a local gradient structure that agents are gonna, at every step, do something like this. So they would be at time t, they would exchange xj's of t, just like they do it in this consensus algorithm. They send to each other these values. And then at the update time, every agent will make the same idea from consensus, makes its own convex combination of the received xj's from the neighbors. And remember, aij's are zero if j is not a neighbor of I. And then it takes step along its own objective function. So it's very simple, just gradient method, except instead of moving from the point xi of t, agents are gonna mix their decisions and then just follow the direction of the gradient. Step size is typically like alpha step size is positive. Now the alternative, that was originally what we proposed, but then there is alternative to this, which is very simple, meaning it falls about, the algorithms almost behaves the same, but the second version here is somewhat nicer in terms of errors. So anyway, alternative is here, mix first the decisions, but when you're updating the gradient, move from the mixed decision as opposed to from the just the most recent iterate xi. So the difference between the two, I guess I didn't put that in notes, but there is a Professor Ali Sayed, and he's now in EPFL, I believe. He has a different names from these for these algorithms. One is adapt, then combine, and then one is combine. I think it's this one, the first one, and the other one is combine then adapt, because first you combine the decisions and then you're moving along the gradient. Anyway, so there is another name that comes with them, but I don't label them. I just call them first and the follow-up. So how do we analyze this algorithm? The analysis becomes really, you just follow the analysis of a gradient algorithm. It gets messier because of the presence of this mixing. But at the bottom, at the end of the day, you can prove the result that's nearly the same in terms of how the algorithm behaves as you would just have a standard gradient. So under assumptions that, and of course, graph is connected but we have extra assumption here that matrix A has to be doubly stochastic. I'll return to that. Because I didn't assume some special Lipschitz property for this process to work, you need gradients to be bounded. And the step size assumptions are standard what you get for any gradient method that uses diminishing step. And these are well known, so I'm not going to spend too much on it. And under those assumptions, you can prove that the iterate sequence produced by any of the agents converges to a same point, and that point is a solution to a solution to the problem. So we don't know which of the solutions will be picked, but we know that all of the agents iterates will go to the same one. In terms of the rate, one can analyze it, and we get basically the rate is slow, which is very, again, common for such methods because of the diminishing step. And because of the impact of the network, we get a log t term extra as a loss in terms of slowing compared to the centralized algorithms. So those two results basically just say we lose a factor of we have an extra log t factor. Now the part that I want to discuss is basically two things. First is, why do we need matrix? Well, I have here, sorry, there is no index of time, because the result we have here is really for time varying matrices. We can prove it. So, but I wanted to make it simpler. So this is, the matrix A is doubly stochastic. So why do we need that? Why is that important? And we don't use particular knowledge of the graph here. So how the graph, one can prove the same result even when the graphs are changing. And I'm going to come back to this result because there is actually a work by Rogozin from Alexander Rogozin. He was in Sasha's group when I was visiting MIPT, and he came up with a work that actually shows some nice results and takes into account how the graphs are changing, imposes certain conditions. So I'll revisit this. And then bottom line that I also want to address is that because the effort lately has been into, among other things, it was to speed up these algorithms. So the question is how to move from the question is to move from a diminishing step, because without that we cannot get a faster convergence. So why is the need for the matrix A to be doubly stochastic? It comes from the analysis, which I'm not showing you here. I'm giving you just an intuition. It turns out that if we just use A being row stochastic, which is actually good for the consensus, but if you are optimizing on the top of that consensus constraints, then your algorithm would solve this problem you are not minimizing summation of FIs, but you are minimizing somehow skewed function, which is a weighted sum of the PIs where of the functions FI, where PI here, or the vector pi, would again be the Perron vector. It's the left eigenvector of the A, which is that steady state distribution vector. So that's why if you want to solve the original problem, then you want these pi i's to be all the same. So what you really want is that left eigenvector here, pi, to be this uniform distribution. And one way to ensure that that happens is to use the doubly stochastic matrix. So that's the only reason why we use doubly stochastic. If one can come up with another maybe structure in the matrix, say, that guarantees all pi i's are the same, especially when the matrices might be changing, then the result would hold. But in the absence of that knowledge, we impose the doubly stochasticity. Now, the other part is that this algorithm, as I presented it, heavily depends on the fact that, so if you want doubly stochastic matrices, then that's doable and one can construct them on the go, even for the time varying graphs, as long as the graph is undirected. But when the graph is directed, we would have a difficulty here because we have no way of constructing easily doubly stochastic matrices on the directed graph. And for that reason, there is a paper, there are some literature here that are pointing to such problem, or how the, what I call it, balancing the digraphs becomes difficult, involving, and it's time consuming. So we came up with alternative direction where you just, for the directed graphs, you have a different algorithm that takes care of the consensus. And that's so-called push sum based consensus. And I'm not going to talk about it today because I don't think I have time. But so one can bypass and handle the situation on the directed graphs by using a different algorithm, basically, for the consensus part, and then combine it with a gradient. I think it's more important, I want to move into part that's probably lately much more drawing attention, is that speeding up the algorithm. So the problem with our initial naive method was that it turns out it's not going to work it's limited, and it doesn't is in general work if you fix the step size to some constant. That's how the algorithm would look. And now if you try to imagine, suppose you are lucky and xi's converge. So you write down what is in essence, a steady state equation for this equation here. And you end up seeing that if that's the case, then with a fixed step, it turns out that gradients, if the algorithm would converge, it would require it would imply that all the gradients of the individual functions are vanishing at a limit point, which is basically saying algorithm that we proposed would work with a fixed step only if all of the component functions that are involved in the sum have a common minimum, which is beats the purpose, right? We don't want to have a limited domain for the algorithm. So the problem is basically, at the end of the day, we said, okay, in this update, we are not going to be able to achieve faster algorithm because we need to fix the step size. That's all of these faster algorithms have fixed step sizes, but the algorithm still remains valuable for the cases when you have noise. And I'm going to leave it at that, but it's not going to work for any acceleration if you want to do fast. So now we look how can we go about now solving this problem, but we now want an algorithm that has ability to converge to solutions with a fixed step and then take advantage of possibilities to meet the performance of the centralized methods. So when you look at this problem, and it's reformulated in this with agreement constraints explicitly written, what you get is you just, which for time being didn't pay attention to the desire to solve it distributedly, this problem is just equality, linearly constrained equality convex problem. And one can approach it through the dual, and that was done with, in collaboration, actually with two of my former students, in collaboration with Sasha several years back, and paper just got accepted. So we have done that dual approach and show that you can look at the paper, we can meet the performance of the centralized methods up to log factor. But today I want to discuss, maybe Sasha can talk about that approach. So it's the dual based. I'm interested in discussing primal algorithm that would go, that would not try to go for the dual. And the reason being, precisely, if you want, okay, if your graph is static, that might be the right way to go through the dual. But if your graph is changing, that means these agreement constraints are going to start changing with time. So in the dual space, what you end up seeing, you're going to be minimizing functions that now depend on time. And then it becomes a little bit harder to handle the cases when the graphs are time varying arbitrarily. And that's really the work that I mentioned by Alexander Rogozin is exactly dealing with that. And he really did a great job. He manages to show to what extent the changes in the graph can be tolerated and get still a good performance. So this is why I'm looking, saying, aside from the dual, how else we can go in a general setting that we can handle the graphs that might be time varying. And it turns out there is basically when we look back in the original algorithm, we can notice where the deficiency was, because the algorithm was very naive and somehow didn't treat this, it really focused on collaborating on the decision space. So basically making convex combinations of the decisions. But it was somewhat selfish and myopic, if you wish. It only moved along the gradients of the individual functions that are seen locally. So as if the agents are aware of the system, they want to help each other with the decisions, but they don't want to help each other with the directions. That's basically how this equation reads. So based on some other work that was related to some kind of estimates, it turns out to think of the agents actually being a bit more aware of this system. So if in that case, they should be mixing the axes. I'm talking about this first equation here. So let's consider change in sense when every agent now has its own state decision xi, and it has an estimate of what the system gradient might be. That's it. And then treats both variables the same. So what they are saying is like, if they are estimating, collaborating on axes, why they are not trying to estimate the common directions jointly as well? And that's really the change. So instead of the selfish gradient, we now have an estimate of what the system gradient might be at a given time, at a given iterate. And then the update of this direction follows the second equation, which says they're going to convexly combine their prior decisions, but every node will also bring an innovation term, which means in this term, what they are doing, they are removing the effect of the prior gradient and bringing the effect of the newly computed gradient. So as if this is sort of a correction term. And it turns out, so this algorithm basically tracks in this iteration here, tracks the system gradient in a way. And every node has its own mechanism for meaning it's the same algorithm, same kind of update, except they're using their local information that differs from node to node. And the name of this algorithm was meaning, sorry, the name comes strange to be. It's called digging. It's one of my postdoc who worked and developed it. And this is a related literature, and I have to mention that we kind of stumbled across a couple people who pretty much use a similar idea, but for different purposes and in different places. So more closely, probably the closest to that work that we had was this work by Gesaldo Scutari at Purdue. He has a sequence of papers in which algorithms he names, then Next and Sonata. They have they're using tracking mechanism in a similar way, but his work was for the Next was more focused on non-convex problems, and scheme is more general. While we were chasing the rate, but we have, I would say, the idea of using the tracking is also present in these papers, so I gotta mention them. And now, what I'm thinking for the time being, so now I have a time varying graphs. So now the algorithm is really the same, except the graphs could be time varying. We still have the requirement. In this case, we are working with undirected graphs that might be changing. Matrices of mixing have to be doubly stochastic for a reason we saw earlier. And every time the graph changes, the matrix A is also missing index here. Sorry for that. It's compatible with the graph, which means that positive entries are only on the links that exist, and there are zeros when we don't have links. We use step size alpha that's common for all of the agents. And I'm aiming at showing you the result, which is no easy to do, but what a main message from this slide is that under certain conditions, we can prove that this digging algorithm with a sufficiently small step size has a linear or geometric convergence rate. Under the assumptions that we use is that the objective function, the sum of the functions is strongly convex, and that each of them is Lipschitz continuous with a certain constant. Under these conditions, critical part is that we also need additional assumption on the matrices here. Let me not bug you with that, but the problem in this case has a unique solution, and the sequences that are produced are all converging to that solution with a rate that explicitly to write this, you should look at the paper. But this is on a high level saying that with this alignment of the directions and very careful selection of the step size, one can achieve the linear or geometric rate, which is actually matching the performance of the centralized algorithm. However, the parameters that enter into the equation when you need to determine the alpha are not all easily computable. So it's really a theoretical result. And to give you just a little flavor what that result looks like on a specialized case is like if you are particularly considering the so-called lazy metropolis matrices, which are defined by using the degrees of the nodes, and that's exactly the structure you have here. Then with the step size given in this equation here, you can get a bound. This is the bound of the number of iterations needed by the algorithm, various parameters of the problem, to reach an epsilon accuracy. So B is number of times you need for the graphs to be connected. So this is much more general than I was talking originally, but just to give you a flavor that this is by no means easy to parse. So the results are there, I would say, more to kind of guide us perhaps of when we are designing these algorithms, designing even maybe the networks. But in practice, if we want to implement, if we don't know the graph, we cannot really find a good step size. We need information from the graph. In this case, let's see, where is that hiding? In this case, the information is hiding, not here much really. it's hidden in some kind of other constants. It's not here because it should depend on the degrees as well. Again, the details of this, you can find more on that kind of particular ranges of alpha that work. It's in the paper that just showed up a couple of years back. So where is the problem with digging? It goes back, meaning now you can have an algorithm. It may not be so easy to determine the step size. You need to know a lot of things. But our bottom line is that we are still kind of using this doubly stochastic requirement. So if your graph is if the graph is directed, we are running into the same problem we already saw a bit earlier. So what happens is that the couple of these postdocs I had that year, they realized actually you can modify this digging algorithm in a way that you can bypass the doubly stochastic requirement. And it turns out this is the algorithm that they term push-pull. And it is really built based on the insights from the digging. And this is the one that I'd like to discuss in a little more details. So the algorithm currently is analyzed only for the static graph. So we have static graph, but at this moment, we don't care whether it's directed or not. So it could be, I will assume it's directed because it's more general, and we'll assume it's strongly connected. And then what agents do is something, so they're gonna still be exchanging the axes, meaning the decisions on the state and the directions, but they will exchange these things a bit differently. For example, every agent will send xi of t now to all of the out neighbors because those are the only links that are leading out. So for every link that goes out of the node I, agent I sends xi and receives xj only from the incoming neighbors. So that's simply just following the flow of the link, direction of the links. However, when it comes to these updates related to the directions GI that they're gonna using in the algorithm, situation is different. Every agent I will take this, its value GI, count how many outgoing links there are and count itself and give a portion. So it's gonna send CLI, scaled version of its direction, to the outgoing neighbors, where these CLIs are such that if you add them all up across all else for the links going out, these numbers add up to 1. So basically, as if taking the different fractions of 1 and sending to the outgoing links and itself, but all the weights of the scalings have to add up to 1. So that's the change. Because from the digging, the situation was there differently. And now and updates after that remain the same, similar to digging except for one twist. I now call the matrix, for the mixing matrix of the decisions X, it's gonna be, the weights are R, so node I decides on these weights. And these weights that govern mixing of X's will be still assumed to be row stochastic. So all of these Rij's add up to 1 if you add them over the J's. However, the mixing of that, what used to be here, the same matrix, now is the, sorry, again, there should be no index K. It's a matrix C, where now C is a column stochastic, because agents, when they receive these portions of the CL, what is that gonna be, Cij, Gj, they're gonna just add them up. They're not gonna do anything. They're not gonna scale them, meaning they're not gonna give any weights to them. They're just gonna add them up. So at the end of the day, to kind of write these equations a little more compactly, we do the same. We introduce Rij0 and Cij0 for the links that don't exist in the graph. And where did I do it? Where did it go? Oh, and we're gonna end up using the algorithm where R is row stochastic, and it's easily now constructible because agent I decides on the weights. C is column stochastic, which is also easy to construct on the directed graphs because the agents who are sending the information, they are constructing that column on their own. Algorithm has a specific meaning initialization. It can start with any initial values in terms of the decisions, but the gradients have to, initial directions should be initiated, which seems very natural with the gradients of the local functions at that initial point, which is all good. So what I want to mention here, I'm going to check my time. That's the work we did really in this paper for the Series C, and now it's going to show up just accepted in TAC. And it turns out that actually we were very close with some modifications and very similar, somewhat similar updates that in the group by Usman Khan were done. And probably the closest paper to that relates to that is this last one here. Actually, we had it was also, I think, presented at CVC. So how do we analyze it? Meaning, I don't know if I have time to show you. I have about 10 minutes.
We often we have 1 hour and a half, so you have enough.
Okay.
You have enough time, yeah. So take your time, please, and do not worry.
Okay, thank you. All right. So one part is that kind of I wanted to have a few slides here. Is that because when we look at this algorithm, it's like where on earth the intuition came from, and it just. I could follow everything until they were using these row stochastic matrices, but all of a sudden now, it turns out you can use row stochastic things for the decisions, but on the directions, it sort of doesn't matter. You go for you want structure, meaning you need them. Why should be working? That's the bottom line. So this slide, a couple actually slides in this direction, try to understand why would the algorithm work. So I will focus here on a very simple scalar case, not because it's complicated, meaning it's just notationally more complicated to kind of write around with the matrices. So I'm going to show you on the scalar case. It just applies to every coordinate in the vector, so you can move it easily to a vector case. So first, let's define these are scalars, let's construct a column vector as a decision vector, right? So now we probably want to minimize is this function f of this bolded x, whose coordinates are xi. And if you want to write down the optimality conditions for this problem, then this is what they become. What they are saying at the optimum, and by optimality principle, you get it straightforward. The optimal solution has to be of this form, which is what we already know. If the consensus is to be, consensus is obeyed, then all the optimum has to happen at the single point, A star. And these are just copies of the same point. And also, by the optimality principle, we need this gradient. We need this condition, which basically says the sum of the gradients of the original functions would be 0. So that's the optimality condition. And now we look back and see, okay, what would happen if in our algorithm, which now we wrote it here in a kind of compact matrix, using matrices, row, stochastic, and column, see what's going to happen if there was a limit. Suppose the algorithm converged, what would the limit point look like? And does it correctly solve the problem, and what is doing in that case? So I'm here assuming that suppose we were lucky and X sequence has a limit, which is now X bar. G sequence of the directions also has a limit, which we get to be G bar. And these are the equations that govern these are the basically steady state. knowing that C is column stochastic, now information from the graph starts telling us some additional pieces. Since C is column stochastic, it's compatible with the graph. It actually tells you C is primitive because we also have diagonal, non-zero on the diagonal of the matrix, non-zero entries. Then this matrix, again by this Perron-Frobenius theorem, would have a unique vector pi, probability vector pi, with all positive entries that satisfies this equation. It's actually the left eigen, no, this case, right eigenvector for the eigenvalue 1. So that tells us that since G satisfies the same equation, then G must be collinear with that vector pi with some constant C, some scalar C. Now we look at behavior of the x's, and we find that from this equation, if you just move the things around, you get that this is the condition that's satisfied between them. What this says is actually that, how does it, the right wording is that this vector pi lives in the range space of this R minus I. And now it turns out that when these two matrices are such that the only thing that is common to this basically null space of I minus C and the range space of R minus I, it's only zero vector is in common, then you get that from there it follows that C must be zero, so your G bar must be zero. And from there you get that now X satisfies this fixed point relation. In terms, again, now we go back to R is now row stochastic, compatible with the graph, gives that is connected, that gives us that R is actually primitive, and it has a unique, this vector of ones is the unique up to a scaling, right eigenvector of R, which tells you that since X bar satisfies that equation, then X bar must be collinear with the vector of 1. And this gives us basically the guarantees that two things for now we have. That consensus would indeed happen. This is what that first condition on the optimality. But now we need to check what's going to happen with the gradients. And here is that, I'm going to return for a second. So to understand what's happening in the, to show that this second optimality condition is satisfied, we investigate the sum of the directions. So going back here, if you apply the vector of ones here, because this is column stochastic, you are going to get some of the directions here and some of the directions here. And there is something here that's going to cancel. So by studying this equation, actually, if you use induction, by induction, you can prove, and this is a step I didn't do, if the matrix is C is just column stochastic, you can see by induction that this update will guarantee that some of the gradients or some of the directions will always match this sum of the gradients. So that's something, it's kind of two-line proof. But that would mean that in the limit, some of these directions will indeed be equal to the sum of the gradients at the limit point bar. And we already found that G bar is 0, so we get the second condition to be satisfied. And this gives us exactly the optimality condition. So what this tells us that, so now if we manage to construct properly the process to converge in this push-pull structure, we have guaranteed that the points that we will reach are indeed the solutions of the problem. And the way we want them, consensus and optimality. And in this part, I'm going to give you a little more of the flavor of how the analysis of the method looks. Because actually, when one of the, actually 3 postdocs were working on this. But the proof that first cut they came through, and it's still there, it's published that way. I had a very hard time understanding what it was very, so why I wanted to understand every piece of the analysis. Because I'm thinking if we ever want to extend these things, currently analysis works on a static graph. if you want to extend it, you need to understand the mechanism of what's the basic intuition. And if you know the basic intuition, then you can push it. And I was failing that. From the original paper they wrote, I was not being able to see how you move this now to a time varying case, because it was just, I had a feeling, it had an intuition that I couldn't see how it can be moved in a time varying case. So there is another paper, and I'll mention it briefly. I'll mention it in a few slides down the road, that when I read that paper, which is from a different group, it just dawned on me. And what I'm giving you here is not exactly how it's given in our paper, but it's more of something that, of combination of the things that I've seen from the other paper as well. And it just seems that, okay, so what is important in this? What is kind of the key part? Key part is that analysis of the algorithm doesn't follow one, you don't pick one, let's say, Lyapunov function and look what's happening to it. No, in this case, it looks at three functions or three quantities in a way. And now that was the first difficulty. Identifying these three may have not been maybe too hard, but then the question is, when you measure these, so these come to be some distances, right? There are some distances between points, iterates. But the question harder than the first one was actually picking up the right norm in which you need to measure the progress. And that, the insight of which norm to choose, comes from the structure of the matrices R and C. So that's the difficulty of the proof. It's identifying right ways to measure the distances, and they are not the same for the X variables and, let's say, the directions of G's. So I will just list the assumptions under which you can actually prove this. First, let's say, of course, graph has to be connected, strongly connected, because we assume it's in general directed. We construct these, have these matrices R and C that are, as we define them, they have to be compatible with the graph. And R is row stochastic, that's why I use R. C is column stochastic. So we assume that each function has Lipschitz constant. Each component function has the same Lipschitz constant, which is not hard. If they differ, you just pick the max. And the other assumption that is somewhat different than if you look at the papers there is, it turns out from what are we gonna do here, if I have a common step size alpha, it's enough to have the sum of the functions to be strongly convex. You don't need each individual function to be strongly convex. And then you take these vectors that keep coming at us. Perron vector, which is basically left eigenvector of R, represents a steady state distribution if you want to view R as a Markov chain transition matrix. And all the entries in this vector are positive. And this vector is unique. Once you normalize it, it's unique. Similarly here on the side, because R being row stochastic, R will not, R applied to a vector of all ones will give you that vector back. So we know what's the left eigenvector. This is the right one. That one will play the role in measuring distances of the X variables, because this R governs the X variable mixing. So now you just kind of twist, top this, kind of transpose it. If C is column stochastic, then I have a unique right eigenvector because graph is connected. And this PC is also probability distribution, and all the entries in this vector are positive. And then you construct averages, weighted averages of X bar. And these weighted averages are really summation with these, weighted by this pi R. Remember, R governs the X variables. So this is just weighted by the pi R, and you basically add up all of the iterates xi. In my case, they are scalars, so I get here just a number. And then the first thing you measure, one of the things you're gonna use as a measure of progress is you look how this is like, what is like center mass of all the axes. And you look, is that center mass gonna move toward the solution, and X star is our unique solution. So that's behavior of the averages, weighted averages. Second part you need is that how the variables Xi themselves are away from this weighted average. And this is basically, you can think of this as a variance in a way, or a dispersion. But here, because these are weighted averages with pi, we are also measuring this weighted average in terms of pi. Basically, if you square this, you're going to get this to be kind of what looks like a variance of in the vector x with respect to its weighted average, but it's a weighted dispersion in a way by the same vector. So this is the second quantity. And last one, you just similar, you do kind of what would look like an analog for the G's. However, here, because of this column stochastic behavior, things are a little bit tipped differently. So here you are looking at the distance of G's from some S of K, scaled version of the limiting vector. This is really something that, it's not limiting, sorry. This steady state, the other, this distribution for the C. And that case to scale, to look this way, it's just because you're here inverting them. It's some rescaling when you're doing the analysis that this works perfectly. So rescaling it this way, it just does the job. And S is just a summation of all the directions. So once you take these quantities and look at how they relate from step 1 to step 2, you get this inequality here is component wise. So we have a matrix and the same 3 quantities on this side at a prior time. And I think I have a typo here. This should be S, not a G bar. This is S, S of K. So the whole hurdle in the analysis is really getting out that matrix out. And I didn't want to give you coefficients because there would be just a long list of constants that are not that exciting, meaning you can do it, but I don't think I can explain them to you. So roughly what I'm capturing in this, the structure of the D, what matters is that on the diagonal, you're gonna have contraction with the choices of alpha, and here contraction with the choices of alpha. What are these sigma 2s? Sigma 2 is the second largest singular value of a matrix R. And because of the structure and the connectivity of the graph, this R matrix has second largest singular value is less than 1. So that's why this number, I call it contraction, because here I have a number less than positive, but less than 1. Here with alpha, we can control it. This part is, oh, sorry. Yeah. I have another more typo. The order of these two should have been switched because this is governed by this guy with the singular value of R. This is governed by a contraction in a way, which is this guy coming from the fact that you have strongly convex functions with Lipschitz behavior. So this is something that's common to gradient methods. So this, with the step size, you can get a contraction there from the well-behaved function. And this term is also, can be contraction if alpha small enough. Well, this is also a number that's less than 1 because similarly, the singular value here is less than 1, the second singular. So now if you look at the structure matrix, given the swap here that I missed to do, you can see that basically, if you study for this process now to converge, you would need the spectral radius of this matrix to be less than 1. And it turns out that you can control that spectral radius with the proper choices of alpha. And that's the rest of the proof that I'm skipping. And as I mentioned, you can find some of these details in the paper that the postdocs wrote a couple of years ago, but it just got accepted this actually last month. And additional insights you can really get from this paper that was presented this last year at CDC, which they are building on the proof that this Pu, Shi, and Zhu constructed, but they're extending this to a stochastic method where you, instead of the directions, when you have the gradients, you are using stochastic gradients. And they assume, you know, like we typically do, there's some bounded, well-behaved process in terms of unbiased estimates and bounded variance. But I found their proof to be, it's not perfect. There are details you can tighten up, but it gives you this understanding of why these distances should be chosen. It basically that they have they have more insightful details than I learned from my own crew that was working with me a couple of years back. So, so what I'm excited about this, because this particular paper opens the door with some of the insights from there that this analysis could be extended to time varying case. It's going to be hard because these guys are going to be time varying as well, but it's doable. It's doable. And I would, oh, I'm almost a little over. What I want to sum up is that where are the things going lately? Meaning I've been seeing so quite an effort to accelerate. And there are, actually there is work, one of, I forgot that, I didn't put here. Bach, so what is, now for a second I may not remember his name. Francis Bach at, he has actually other works on acceleration when he's really trying even to match the constants. So that's, I think there was a work by him and Skaman, I don't remember right now, I forgot to put it here. But other than this speed up, in which there are many groups kind of looking at to kind of meet the performance of the centralized methods, there are other directions that are kind of also picking up. One of them was solving non-convex problems, and I don't think it's fully explored. So there is some related work, but much more of the work is still sitting in the convex universe, just like the ones I was discussing today. Asynchronous implementations turn out to be desirable for the reasons because if you want to implement these algorithms in real maybe setting when you have multiple machines with their own data and they need to communicate and do all of that over a network, then synchronizing that computational this timing of the iterations when you're going to do them, it becomes a very complicated issue because maybe one node has more data, then it takes it much longer to come up with the updates. The other node maybe less data, more power. So there is a lot. So in the way we treat these agents, they are pretty uniform, as if they're all of the same capabilities. And often that's exactly what it's not real. So that's where the asynchronicity kicks in, as well as delays come in, because communications, depending now which kind of agents you are talking about, delays could be significant, and we have no delays in everything is perfect, everything is perfectly timed. So that I'm here mentioning, there is also work with Alex Olszewski, who's recently looking a lot into how these algorithms scale with N. And he has some work with Shipu as well as looking that there are some cases when asymptotically the scaling of the network disappears. So it's not actually affecting asymptotic behavior. And I think some of his results are quite interesting. And there's one more that I'm going to mention, which has to do with basically securing your, so these computations, if you are really dealing with a certain data, and data is sensitive for privacy violations, there is maybe more people, but I know of Yongkyang Wang, who works on the privacy issue and not trying to, meaning you can think of privacy in a couple of ways. You might think, oh, okay, I'm just gonna code everything I need to send. I'm gonna, or what I put a sort of like, what they call that, crypto code, right? Encode it and send it over the link securely. That's not the privacy they are thinking of. It's more of saying, can my computations be such that when I send things out, even without coding, somebody can really see the numbers, but they cannot get what my X state is, for example, or the direction is. So he's looking at algorithms that naturally hide informations about the functions, basically. And there's one more direction, which is also, it has a pretty big group these days that are looking at cases where, and these are different applications. They are not necessarily on machine learning, meaning not this case that I was talking, like classification issue, but rather there are systems where if you have a node that's basically malicious, or somebody just hacks into your system and wants to manipulate the data to purposely lead you to wrong answers for whatever reason, their algorithm, they are now considering kind of understanding which of these algorithms is the most robust to some of these attacks. And there are also works that they're just measuring the effect of the attack. And there are others who are trying to kind of take a more proactive way to say, it's not just I'm gonna sit and wait and let the damage be done and just measure how big it's gonna get, but rather I'd like to detect if there's anybody who's purposely sending me just false information. And there are mechanisms in some cases that you might be able to learn which agent is not good, and you might like to cut it out of the network. So these are the kind of more or of a trends that go in some different directions other than us when we just think of, oh, I just kind of want to, I'm looking for speed in algorithms. There are other issues that people are actually closer you are to an implementation of these algorithms, many of these other issues will come up. So it's not necessarily just the speed. And with that, I'm thanking you for the time and for being here today with me. Thank you so much. I'm taking any questions whenever you have.
Thank you a lot, Angelia. It was a very nice talk. And so I see the hand of Oleg Amisov. And so, Oleg, you can unmute you.
Hello, thank you for a very interesting presentation. I have a couple of questions about the matrix A. First, you said that matrix A can be non-symmetrical.
Yes.
But that means that each node knows that there are some nodes with smaller indices, some nodes with larger indices. So there is some centralized system that enumerates all the nodes, especially when graphs dynamically change. How can you implement that?
Okay, so, okay. All right, so to put it this way, for the technical analysis, it's not needed to be symmetric. But in reality, if I want to, so let's say graph is not directed, undirected, and we want to construct the doubly stochastic matrix for that particular graph. There is a way to do it, but when the agents exchange the information, they have to exchange something more. So let's say I and you are going to decide on AIJ, and you decide on AJI. But to coordinate it, because I want to construct a doubly stochastic, what we can do is I'm going to tell you, look, I'm planning to give you 1/2. And you tell me, yeah, I'm planning to give you 1/3. And that's the part that we can exchange when we exchange the x's. We kind of exchange planned weight. But when I see that you're sending me 1/3, I'm thinking, well, I'm going to give you 1/3 too. I pick the minimum. So we can, by that, you apply the same rule on your end. You take the minimum 1/2 and 1/3. I take the same here. We both going to give 1/3 on that link. And once we are done with these weight assignments, with these exchanges of the planned weights, what I'm calling them, then whatever is left to the value of 1, I'm just going to give it to myself. So you can construct a doubly stochastic matrix on undirected graph on a go.
Mm-hmm. Ah, I see. So
But
it doesn't depend on index, it depends on the state of the neighbors. Oh, I see.
But you need to kind of share what you plan for the weight to the neighbors.
Mm-hmm.
So you have extra piece of information that you have to put in the system, basically.
Also, one more question. The entries of the matrix must be strictly non-negative. Is that something that is dictated by external constraints, or is it just for the method? Because stability of the method can be possible even if the entries are negative.
Actually, you are completely right. And there is a paper by Boyd and Lin Zhao. They were looking at what's the best mixing weights. So in our proof, we heavily depend on the fact that it's positive because of these weighted things that we are constructing, and then weighted distances that we get. So, but for the iterative process there, you don't really need it to be non-negative. And it doesn't have to be. The only thing is that the analysis as it stands now heavily depends on the existence on that eigenvector. And to
so you basically need to have eigenvector of 1, so all the variables will
that one you get, but an analysis also depends on the existence of this Perron vector pi.
Ah, yes.
Which I don't know what that vector would be if you just allow, because aside from linear part, when you look at it, I don't know how that limit would look when I want to use the steady state pi for the measuring purpose. Not for the consensus, but later when I want to do, when I want to basically do this centering and weighted deviations from that, then I'm losing the power of analysis there. Not for the consensus, it's for the when you add the objective. At least the path I'm taking, I just have hard problem with that.
Mm-hmm. I see. And the last question, did you consider constraint problems, especially inequality constraints? If we have, for example, if inequality constraint includes states of several agents, like x1 plus x10 less than something, but x1 and x10 are not adjacent.
Yeah, we have something like that. Actually, let me back off. Not in that explicit form. We had constraints, we had done some work on constraints where agent I may have local constraint set xi. And then you can do some of these basic naive method by using the projections, but you need special conditions that can lead you to showing you can solve the problem. But I don't, let's say, what other work I can relate to is, we had a paper and there is also work by another guy, but the paper is not out. It got just stuck in the middle of everything. What's the name of that? I forgot the name. I'm trying to, but it's more of like saying, oh, what was that? We call that problem resource allocation. That was the name. That's the word I'm looking for. So there is a paper. There is a sequence of papers by what's his name now? Oh God, sorry. He's at Pennsylvania State University. I bet. He has some papers when he worked in the distributed algorithms for that resource allocation. And resource allocation are those kind of problems where your agents kind of constraints may depend on the local, it has this kind of additivity structure to it from the neighbors. So there is some result, but not as much, not as much.
Mm-hmm. I see. Thank you very much.
So, any other questions? You can unmute you by yourself. So now there are no restrictions. So
maybe I have just one more question. Could you please go to the page 18 on your slides? It's a
Sure.
method.
Let me see how it goes. Yeah, I'm back. Yes.
So coefficients di, dj here, what are they? Missed it. Can you describe it? Oh, sorry. Yeah, I see now. Yeah. So
yeah, what they call the degree counting. For this matrix to be constructed, agents that's another one construction one can use, where instead of the one that I discussed, like we plan weights and then we exchange them. For this matrix, we need to, I need to tell you my DI and you need to tell me your DJ, if we are I and J, right? Then we can construct this. That's another way of constructing a matrix. That's
so basically, if the bus has a lot of neighbors, it is more valuable to the overall optimization. Oh, I see.
But by doing this, exchanging that and doing this rule, then we guaranteed we can balance the matrix basically. That's another one.
Thank you. Thank you.
Yeah.
We have a question in the chat. Okay. So I can read it for you. Could you please clarify why delays are important? Do the functions vary during time? Question by Mikhail Bakhtirev.
Why delays are important, right?
Yeah, why delays are important, and do the functions vary during time?
I missed the second part.
Do the functions vary, changing during time? So.
Where are the functions changing?
Do the functions change during time?
I understand. Okay. All right. So so there is this. I didn't talk about the case when the functions are changing over time. No, but in some of the applications probably are collecting the data. So there are, at the moment when, the way I'm thinking, you may think the data was already collected. Every center has collected the data. So functions, objective functions at that moment will gonna be reflective of the data that have. So that there's no time. I'm not looking at this model when time functions are gonna change because I'm gonna collect more data so that the change will kick in. Now, why is the delay? Is simply because in different places, so for example, what if this data sitting at different centers, physically, geographically separated? Then how I'm gonna be timing them? So that's one possibility. Maybe we don't wanna do that. The other thing, and this really comes from, I think this colleague of mine, Rabat, who works lately he is in Facebook, and they are looking especially in the delay because they have a lot of computations that are done on multiple machines. But the load on the machines is, so if the machines don't have the same capability, you have to do firstly some kind of loading so that machines can produce your X's or whatever computations about at the same time. But if they are, in their cases, what I understand, if you don't balance the load, you're going to see the delay. Because if I have my component function, maybe 1 million of them at my, I'm a node and I have 1 million of them, it's going to take me a long time to come up with a gradient. And somebody said, other node may have only 10,000 of these data points. It's going to easily compute its gradient. So the discrepancy comes in the delays from, if you think of these machines as workers, these workers take different time to complete the task. Every iteration is sort of a computation task. And that's one source of delay. Second is communication. If these machines are, nodes are not connected, so that communications don't take time, then you can see the delay comes from computations. In some places, it's maybe the physical link that causes additional delay. Because I sent something, but the link failed. That is the same as not talking at that moment to that node. This may be more applicable to sensory networks than maybe machine applications, machine learning.
Yeah, and so do you aware of some results for time varying distributed optimization where in algorithms people try to incorporate some compressions in order to send less information, for example?
Oh yeah.
To accelerate the training.
I understand. I haven't seen it.
So because for static graphs, I saw some papers, and yeah, there are some papers handling this situation, but for time varying, I'm not sure.
I'm not sure what would be the difference. Why is that?
Yeah, but
why is it hard? I mean, I'm aware of some work, but doesn't go to optimization part. It's more of, and maybe it's applicable. I never really looked at that. It's more of saying this is basically this, let's say, go back to the consensus protocol, because it's the simplest, right? In terms of there is no objective. It requires sending the entire vector X, which is whatever dimension it is, that's sending a real numbers. And you're not gonna really, if you're looking at actual exchange of information, you're gonna have quantized. It's a digital kind of connection, right? So there is a paper by one of my, Professor Tamer Bashar and another student of his, Rasul Etesami, I believe. They looked at quantization effects, the coding part. How many bits at minimum I need to send so that we can reach the agreement? And then I haven't really looked into, I know they have that, and it's interesting because it turns out it's small. But I haven't read the paper. This is more of like I look at the abstract and I thought this is something I may like to read, but I didn't read it. And I'd like to know about the paper you're talking about.
So I'm talking, so probably it's the first paper that comes to mind, it's by Anastasia Koloskova and this group of Martin Yagi. They considered method like Choco SGD, but they considered case of static graphs.
That's okay, because the emphasis is on something else. Okay.
Yeah. And I was just curious about some why. So I was curious about some generalizations for time varying graphs for that to have complete picture of what is going on, and yeah.
Yeah, I'm not aware. As I said, if you don't mind, send me the link, because
Yeah, okay.
I know yeah, about Yagi, but I don't know exactly how I'm gonna find the paper.
Yeah.
Yeah, I'd like to look at it. I don't, yeah. But I can't tell how hard it would be, is it? Because I don't know what the principle they're using.
Yeah. And also you mentioned on the last slide, you mentioned some other directions of work, and I'm curious about non-convex case. Yeah.
Yeah. Yeah.
So for are there any results for that combining some optimal non-convex method, optimal for finding stationary points like spider or spider boost? And it's for they were designed for finding some problems, finding some non-convex problems, and also recently I saw on arXiv some papers, some distributed versions of spider boost, and when and the same question is about time varying graphs and this kind of thing. So what is the state of the art there?
So for the non-convex problems, the first paper there was really Tanya Tatarenko and Turi. And I think they did there some stochastic method for, I think it's time varying graph involved there, but they're using this kind of, the first method that I call naive method. It's that approach. So the paper by Scutari actually has 3 papers, I think, in that sequence. And the papers that are labeled with next in the name with Di Lorenzo, there are 3 papers that they develop. I think maybe 1 journal, 2 conference, something like that. Anyhow, they do look at convex, non-convex problems. I just don't recall. My feeling is they do have time varying graphs. No, they do time varying graphs later in the sonata part. But what they do in their setup in this next that I remember vividly was it's meaning they did a generalization that allows them to analyze a lot of things within that framework.
Yeah,
and what is
interesting?
What the bottom idea is that what we usually do is when we are taking the gradient step, we are just basically using a linearization of the function, whether it's convex or not. That is what we are doing, right? You just take the linear and then you have this, kind of argument step, right? In their case, they are taking not a linearization, but they are surrogate, which means any function whose first order information matches and the function value. So 0th and first approximation are matching, but it's a surrogate function, which in principle works. That's what you end up somehow when you are using non-convex functions. Any function would do that 0s and first orders are matching. And that's the power of their result. They really give up a very flexible kind of approximation there. So you don't have to work with a function. It could be something that has the same value and the direction as the function you want. And they give a nice set of examples. So I like that from that endpoint, that it provided something that's more general than what we typically do. Just take the function and its approximation first order. But what I meant to say is that, but the analysis ends up with arriving at stationary points, but not telling more than that.
Yeah.
So that's the part that one can go and maybe try to see what are other options to maybe escape from undesirable stationary points. So in that respect, the analysis hits the standard, basically the block that we always run into when we run gradient methods. It's just That's it. That's how far they're gonna take us.
Oh, okay. Thank you a lot for the explanation. And by the way, according what about the paper that I mentioned? I sent the link in the chat. So
okay. Thank you so much. No, I realize I have to run. I have a dental today. in 20 minutes, I have to make it. But
okay.
I'll be back, meaning in the audience in the background, I'll be back.
Okay, thank you a lot, Angelia.
Thank you. Thanks you. Thank you, Sasha.
And Angelia, thank you very much. And sorry for it was too many questions on the defense.
No problem.
Thank you very much. It was very important for us because when you start your grant at MIPT, it was not such a direction, distributed optimization. And for nowadays, I guess for about 7 students, PhD students, work in this direction. This is the result of your activity. And I hope that we will continue such a collaboration, and some of the students that start to work with you, say Alexander Rogozin, they consider an opportunity to continue work with you, and I hope it is possible, and it lead to some new results, especially in the distributed optimization on time varying graphs. It's a very important thing nowadays. Thank you very much. Thank you very much.
I'll be glad. Yeah, I'm here. And you have a great day. Thank you so much.
Have a nice day.
Bye.
Bye.
Goodbye.
Bye-bye.